Hello and welcome again. In this tutorial, I'll be talking about the I/O ports, of the computer, our 805 SoC system on chip. So this is what the SoC looks like. It has the port A, B, C, and D, which are bidirectional input output clock ports. These are the inputs and this is the data out. So we'll be talking about this in this tutorial. I'll be explaining the the circuit in Logisim also. Then I made a little write-up under it explaining some basic important parts of it. I wish you go through them before watching this video. So this is what the I/O port looks like in Logisim. So here I'll be simulating the circuit to show you how the inputs and outputs works. So but let's go into the circuit and see what makes up the circuit. So this is the I/O port circuit diagram. This is what it looks like. So let me zoom out so you see what it looks like. Then let me zoom in again. So here you have your port A, port B, port C, port D. Then below that you have the port A direction register, port B direction register, port C direction register, and port D direction registers. So these direction registers are used to set the ports to either input or output. So these are the registers holding them. All these are registers. For people who use Logisim, you know these are registers. Then this is the reset line, this is the clock line, and this is the chip select read write line. I'll show you how that third line was generated. But just note it that you select each of the ports, whether the ports or the port address. I explained it when I gave the write-up here. So I was explaining it somewhere on the write-up. So here you will see, let me simulate it. So I've actually added the clock. So now in the write-up I stated explicitly the role this address plays. This is the CPU address. You realize that every sub-circuit I've treated always have an address from the CPU, because the CPU has a common bus where all the other circuits are connected. So but each of them has a particular address on the CPU address. So this particular address is for this I/O ports, for the I/O port sub-circuit. So address 0 is for port A, address 1, 2, 3, 4. So the CPU can actually reference whether the ports or the port directions using this address bit here. So here is address 1, address 0, address 1, address 2, address 3, and I'll show you how it does that. So now take a look at these comparators. So all these comparators, you can see them all lined up here. They are what is used to unlock these multiplexers that accepts data. So this data is the CPU data coming from the CPU. So this comparator checks if the address is equal to 0. That is, if this address is equal to 0, unlock this multiplexer and get the data to port A. The same thing here, it checks if the address is equal to 1, unlock this multiplexer and send the data to port B. If the address is equal to 2, unlock this multiplexer and send the data to port C. So that is how the multiplexer is used to allow this address bit to send data into any of the ports or the port direction registers. So these are the comparators that checks the address the address bits. Then these are the multiplexers. All these multiplexers lined up here are the ones that are used to unlock the input data. These are the registers that store these data. Each one has its own register that stores the data. Then this multiplexer here, this second line of multiplexers here, let me show you where they come from. They come from, to trigger them, they come from here. So you can see that it has a line where all these first multiplexers are connected to it. So what it does is it checks if the IO port chip is selected. Remember, we've discussed this in other subcircuits. All the subcircuit has its own chip select to know if once it's on, it means that the IO port is selected. So whichever port the CPU wants to connect with, it turns the chip select of that subcircuit on. Then this read or not write means when is on, it means the CPU wants to read from the subcircuit. When it's off, the CPU wants to write from the circuit. So we use this NOT gate to check that it is off. So whenever it's off, this and the chip selector of the IO port is selected, then these multiplexers are unlocked. They are the first line of multiplexers that actually allows data to the port direction and the MEM data ports to be open to accept data. So they act as a control here. This chip select read write. The read write is for reading or either reading or writing, and the address bit, and then the actual data that is meant to be sent in. So this is actually how the port data and the port direction is arranged. Now remember, when you go to the write-up, I stated that once the port data is 0, the port direction is what is input, but once the port data is 1, the port direction is output. So I'll also explain how that works. Now this set of these are the port IOs here, and actually this is port A, but this is port B, port C, and port D. So maybe I'll talk only about one port, but that's exactly how the rest of the port is. You can see they are quite symmetrical. This works for port A, this works for port B, this works for port C, and this works for port D. So they are quite symmetrical. So I'll just talk about one of the ports, but that's equally the same for the rest of the ports. So then again, when this address bit is selecting which data to write to, is also selecting which data to read from. So remember, you can watch that is the same address line that went to this multiplexer here. So whenever the CPU enters into reading mode, whatever data here is being read by the CPU and is through the function of this same address. So just the way the address selects data to be written into the ports, the same way it's selecting data to be read from, because it's the same line here. You can watch the same address line that is used to control this multiplexer here. And just the same way, for here is port A data out, port B data out, port C data out, and port D data out. Then these 4 makes up the first 4 of this multiplexer. Then the next one came down and they represent the port directions. This is where they actually came from. Those port directions went up again. The 4 of them, they all went up and made up the remaining part of these multiplexers. So just the way 0 represents port A, port B, port C, port D, the port A direction, port B direction, port C direction, that's how it works for both the input and the outputting. That is whenever the CPU enters reading mode. So then again, so what I'm talking in essence is, while it's selecting a particular port for writing, it's selecting that same port for reading. So it all depends on this bit, this read write bit, to determine what we're actually doing. Are we reading or are we writing? So then again, let me talk about the port IOs. In real life, they are not actually separate output and input. They are all the same one port. Is a bidirectional port. So but in Logisim doesn't have a bidirectional port, so I actually separated them. One is the output, one is an input, and I'll show you how they all work. I explain each of these in the text on the website. So let me first of all talk about this port. This port controls the output. So this is the output and this is the input. This is the output, but as I explained, I told you in real life they are both together. It's just one port serving as input and output. So this port 2 controls the outputting, while this port controls the function as an input. This port controls the function as an output, and this port controls the function as an input. So let's first of all see the port that controls it as an output, which is port 2 subcircuit. So this is what the port 2 subcircuit looks like. It controls the ports acting as an output. So this is the output of the port here. So it has the ability to either turn it on or off. So whenever the port data comes in here, the data to enter the particular port, then the port duration register here is the one that actually insists on whether it's going to allow this port data to go out as an output or whether it's going to block it. So as you can see here, the port data are all set to 0. So all the functions of the port as an output is completely disabled, and we use this control buffer here. So this is a very basic circuit. I'll just test this so you see what it looks like. So when I turn this here to 1, you can see on this here, watch how the individual reactions when I manipulate this. So whatever is in the port data is going to be sent to the port IO on only those particular port bits that are set to 1. So assuming I turn everything to 1 1 1 1 1 1, you see that the only places that on 1 are only the bits where the port duration is set to 1. The ones that have 0 are turned off. You can see they are all X. So it's through the function of this control buffer we are able to achieve this. I know the control buffer is just a basic logic gate. I think it won't be hard solve understanding it. So that's how this port 2 works. So whatever you have in the, so let me do a little bit of simulation here. So assuming I want to set the first 4 bits of port A as an output, that means I'm going to go to the port direction and set these first 4 bits as 1. So let me show you how I'll do that. I'll first of all make sure that I have to select the port A data duration register, which is, we already know that this one is 0 1 2 3 is 4. Port A data duration register is 4. So I'm going to set this address to 4. So that's the first thing I'll do. Then I'm going to leave this read write to 0 because I want to write to the CPU. Then I'm going to turn the ioport chip select on to select this ioport chips. So then I'm going to now set the first 4 bits to 1, 2, 3 and 4. So you can see that the first 4 bits of the duration register have been set to 1. So I've successfully set the first 4 bits to 1, therefore they are now outputs. Now I need to send a data to it. So what I'm going to do, now I've set the duration register, I need to set the data itself. So I'll make sure then I have to select the port A data. Port A data register is at address 0. So I said it's now in address 0. Then I'm going to say, assuming I make everything, let me say 10, 10, 10, 10. Watch carefully. Then next thing, let me turn the chip select on of port A. Just watch that even after manipulating the data in, the port duration register still remains what it is, because I'm no longer communicating with the address of the port duration register. I'm now communicating with this. So now the port A, I've taken this whole data of 10, 10, 10, 10. Now let's watch what is going to output at the port here. So now watch it. The last 4 bits remains disabled because I only set the first 4 bits to 10, 10. So in as much as I have other 10, 10 here, is disabled because the port duration made it to be disabled. Now disabled means I've set it to an input, not as an output. So you can't use this output part of it. So you can only use the input, use this part that is set as an input here. So now let me talk about this ports here. This port here is used to affect the functions of the ports as an input. Now let me go to the subcircuit and you see what it looks like. And this is what it looks like. So it has the ability to switch between the data input and the data output. Now this is our port duration register here. So if is 0, if the port duration here is 0, therefore it is serving as an input, and the data we are going to be collecting is the data from the port IO, that is the output port, the port that is coming in. But if is equal to 1, I'm selecting the port that is coming out from the subcircuit, which is the port data. Now note the difference between the port IO is the input port. The port data is the one that is coming from the CPU that is going out. So unless I set it to 1, so let me give random values to them and let's see which one is going to obey here. So for the port IO, I give it 11 1 1 1. Then here I give 1 1 1 1 1. Then let me randomly turn some ports as in and out. So randomly, okay, let me turn the first 4 as outputs and the last 4 as inputs. So now you see that this first 4 I set as an output is going to take exactly the values. This is it here, and it's going to take exactly this value here. And on this last 4 I set as an input, we take the last 4 values here, and that is what you are seeing here. I just hope this is cleared actually. So let's go back there so you see what I'm explaining here. So what happens is the port duration register comes in, your input, which that is your port, the IO input you are sending comes in here, and then the port data comes in here. So depending on whatever is in the port duration register determines what you'll be sending out here. So meanwhile already the port here I've already taken this 1010, which is this 1010 here. So it's now waiting for me to know what I'm going to give as an input here. So watch, let me give an input here. Let me turn everything here as 1. Let me set everything as 1. 1 1 1 1 1 1 1 1 1. Now watch what happened. The output took the first 4 bits of the ones I set as input, and then took the last 4 bits of the one I set an output. Watch and see that it didn't take this first 4, because the first 4 bits were actually set as an output. So if I input anything there, it doesn't work. So it might be a little complicated because I actually separated them, but in real life, you know, like if you're using an Arduino or a Raspberry Pi, when they say it's working as an input or as an output, we actually know that we are talking about one port that is joined together. But I actually separated it for better understanding, and the fact that Logisim didn't have a separate in-out port. It only has an input separate and an output separate. So this is how the IO acts as a bidirectional input output clock.